Okay, so today we want to introduce logarithms, and we are going to build up off of what we were talking about on Friday. We had a brief lecture on solving exponential equations. And what we saw was our key technique needed to change the bases to be the same base. And as soon as they get the same base, we can use the one-to-one property to set the exponents equal. And as soon as we're setting exponents, whatever expressions appear in these exponents equal to each other, they're almost always polynomial equations. So then we reduce it down to our previous techniques, everything that we were working with, polynomials, maybe rational functions, and then solving the equation from there. There is one problem though, and we kind of saw this on last week's IC. I changed the IC a little bit to change the numbers so it would actually work out in such a way that you could solve it. But with the original numbers given, there was a point where you would have solved for an expression something like 2 to the x is equal to 5. And how do we solve this? Well, 5 is not a power of 2. So we actually cannot solve this with the methods that we were introducing on Friday. So we cannot solve this. So we cannot solve exponential equations by previous methods. If we cannot make the basis the same. So what we need are inverse functions. So we've talked about inverse functions, but we haven't quite seen a whole lot of inverse functions. We've done some basic problem solving of finding inverses of a line, finding the inverse function of rational functions, but logarithms are probably the first big use of the properties of inverse functions. And so remember, when we first started talking about inverse functions, in some sense, what you want to think of as a function as a sequence of mathematical operations. Add things, add a certain number, multiply by 2, square it, raise it to a certain power. These are all some mathematical properties, and I can do a sequence of these properties to create a function. And remember that an inverse function tells us, well, how can I reverse those operations? Can we get back the initial number that we input into this function based off of a given output? And so this is what logarithms are doing. They are going to reverse the exponential process. So a logarithmic function is a function of the form y equals log base b of x, where, just as with exponentials, we have our base is positive, bigger than 0, and we don't want the base equal to 1. This equation implies So I guess let's write one more sentence. So log base b, we'll say this is the inverse function of, let's call it g of x, of just b to the x. And I guess if we call this one, instead of y, let's just call it f of x. So in this case, f of x log base b of x is the inverse function of b to the x. And we know that because both of these are 1 to 1, or because exponentials were 1 to 1, that they have this inverse function. So this is what the function is, and vice versa. So once we have one inverse, the exponentials are now inverses of logarithmic functions. And the inverse property tells us that if I have y is equal to log base b of x, the equivalent exponential statement is b to the y is equal to x. So it's always the base of the logarithm raised to the opposite side of the equation equal to the argument. So whatever the argument, whatever the independent variable is for a logarithm, in some sense becomes the dependent variable. It becomes sort of by itself on the other side of the equation in an exponential setting. So let's do some examples. If we have log base 5 of 125. So we just want to practice computing these guys. We want to practice getting used to logarithms as a function and evaluating them. I know how to square things. I know how to raise things to the third power to the fourth power. If I have 2 to the x, as we saw on Friday, we could plug in different powers for x and compute them. We want to be able to do the same thing for logarithms. So let's get used to it with practicing a few. Give me 1 second. And so what we do is we want to use this property, these inverse properties between logs and exponents. And what we can do is say, well, if I don't know what log base 5 of 125 is, we don't know how to compute it, we aren't used to seeing something like that, let's just call it something. Call it y, a variable we want to use. You can use any other letter if you want. I like to use y. You could use x. And now let's use this property here. So let me actually box this. I like this property a lot, even for my own calculations, especially when I was learning logs, just to have this in mind and be able to problem solve using it. That if I have this statement, then the equivalent statement is base to the y, so it's always the base raised to the opposite side of the equation, equals the argument, whatever the independent variable is valued at. So now we are asking, what power do I need to raise 5 to in order to get 125? And you need to recognize that 125 is 25 times 5. In other words, we will get 5 cubed. And so our y is 3. Other examples, if we have log base 3 of 127th, we don't know what that is, let's just call it something. Let's say it's y. And this says 3 to the y is 127. So always base to the opposite side. And now we've got to figure out what power do I need to raise 3 to in order to get 127. So hopefully some of the powers and exponents are starting to settle in. 27 is 3 cubed. So 127 is 3 to the negative 3. That negative exponent will give us that reciprocal. And so y is negative 3. Here's an important one. Log base 7 of 1. So what does it say? Let's call it x. And this equation now says 7 to the x is equal to 1. What power do I need to raise 7 to in order to get 1? And in this case, we get x is equal to 0. It's actually going to be a very important property. Log base 7, log base b of any base of 1 is always going to be 0. And our last one, so we have log base 8 of 1/4. Let's call it w. We're evaluating this. We don't know what it is, so we'll call it something. And now rewrite the equation. It says 8 to the w is equal to 1/4. So you're always taking, again, base to the opposite side. 8 to the w equals that. If you can at least remember that, 8 to the w, or 8 to the opposite side of the equation, then you can kind of just fill in the other part of where that goes. This one's a little bit trickier now. So our power of 8 to get 4. So we want to choose the appropriate base, and a base 4 may not be the best, right? Because base 4 squared is 16, 4 to the 1 is 4, 4 cubed is 64. It's going to skip over 8. So let's reduce both of these down to a base 2. So 8 is 2 cubed. So 2 cubed to the w gives me 2 to the 3w. And 1/4, so 4 is 2 squared. So 1/4 is 2 to the minus 2. And so now we can reduce our equation to setting the exponents equal. 3w is equal to negative 2. And so w is equal to negative 2/3. So these logarithms that appear, they are numbers. We can simplify some of these numbers if we're given nice enough expressions. I can actually compute this and get either a fraction or an integer solution. But we don't always have that. Like our opening example says, if I am looking for 2 to the x is equal to 5. Well, what's the R equivalent log statement? This is saying the base is always the same. So here we have a base 2. This is saying log base 2 of the opposite side of 5 is equal to x. And that is our solution for x. If it were a nice number, instead of 5, I could use these techniques to actually solve for it, to solve for a numerical answer. But instead, this is what we have to leave it as. So think of it as like square root of 2. Square root of 2, we leave as square root of 2 in our answer. Square root of 10, we leave as square root of 10. Because we can't simplify that. I can't compute it. And if we wanted to, we would have to use a calculator and round it to however many decimal places. This is going to be a very similar process with logarithms. If you have log base 2 of 5 in your answer, that is a number. It's just a number that we cannot compute by hand to get a decimal approximation for it, at least not easily. And you'll learn techniques for that in calculus. So for now, we just want to be able to manipulate these expressions. Think of it like pi. Pi is, again, a crazy irrational number. And whenever we see pi's in equations, we leave it as pi. And that's essentially what you're going to do with these logarithms that cannot be simplified. Just some notational examples that are going to come up. Probably most people have seen, if we write just log of x and don't specify a base, that means log base 10. So all the log buttons on your calculators, all log base 10. If we see this ln of x, means we read it as natural log, and I think some places read it as lan x. I think Canada does that, maybe Great Britain as well. It's called natural log. So if you want to say natural log or lan, it is the log base e, where e, I don't think I wrote this. We'll talk more about e at the end of the course. You'll talk about it in calculus as well. But it's going to be an expression like this, and when we take n for very big numbers of n, as n gets bigger and bigger, this approaches a limit, is what we call it. It's about 2.718. Another number like pi. But we can do examples with this, like if I just write log base 10, or here, just log, let's say 100,000. We want to evaluate this. Let's call it something. And remember, the base is 10, so the equivalent expression says 10 to the x is equal to 100,000. And then you just have to remember how your decimal places work with powers of 10. So that's 10 to the 5th, because we got 5 zeros. And so our x is 5. Likewise, we can do this with powers of e. Unfortunately, because e is a irrational number, I can't write it as a numerical approximation. So we can't even write e to the 5 as a numerical approximation. So when I actually have numbers to an exponent, this is really the reason we're developing logarithms, is because natural logs and logarithms in general help us reduce exponents. So what we'll see tomorrow, or what we'll see on Wednesday, is that exponents will come down in terms of multiplication. So what does this say? This says base is e as well as this base of the argument. So this says e to the y is equal to e to the 5. And so we can just straight up read off y is equal to 5 here. Okay, so let's do a couple of graphs. I'm going to let you guys go ahead and get started on the in-class activity. So what are these properties of logs? They are the inverse functions of exponential functions. So we listed out a bunch of properties that you want to look for in the graphs of exponential functions last week. All of those properties should flip your x and y information. So any information about the x information will flip to y information, and vice versa. So for example, in exponentials, they have a y-intercept of 1. Flip that now to an x-intercept for the inverse function. So we have an x-intercept here, and let's just write it out. Log base b of x is our function. So our x-intercept was 1, 0. And we kind of saw this with log base 7 of 1. By sticking 1 for x, we'll get a 0 for y. Exponentials have a horizontal asymptote, so that will flip to a vertical asymptote. Vertical asymptote. And it'll be the y-axis. The domain and range are going to flip. Our domain for exponentials was minus infinity to infinity. That will now be the range of a logarithm, but the domain will be the range of an exponential. So the range of the exponentials we saw was 0 to infinity. And so this is going to be important. Our domain now is restricted for logarithms, 0 to infinity. This tells us that I cannot take a logarithm of a negative number. Cannot take a logarithm of 0. We can check some of these computations here once we try to graph it. So we'll have one-to-one functions, of course, because we have an inverse. We've got other properties. So base, when the base of a exponential is between 0 and 1, this corresponds to a decreasing function. Same thing with logarithms. So when the base is a fraction, decreasing function. When the base is bigger than 1, I guess it could still be a fraction, but a fraction bigger than 1, it could be, base e 2.718 something something. It's going to be increasing. Most often, we will see bases of logs as integers. We like bases as integers. And if not, even with these fractional bases, you can always turn them into a base where the base is bigger than 1. But the only base we use that's not an integer is usually base e. Okay, so let's graph a couple of these. Let's do log base 2. This one's always easy. We like 2. It's a small base. Works well with exponents. We don't have, it doesn't grow too fast. So, right, we saw exponential growth on, I think, Wednesday of last week, where we graphed something like 9 to the x. And we saw how big it got really, really fast. Log base 2, or base 2 exponents, base 2 logs are both quite nicer. So with exponentials, they grew vertically really fast. The opposite is going to happen with logarithms. It's that they're going to stretch horizontally, and it's going to take a long stretch horizontally with a small gain vertically, is what's going to happen with a lot of these logarithms. Let's pick some values. And let's first start, we always like to start off with x equals 0, and this isn't going to work. Let's see why. So if we try to plug in 0, what does this say? This says 2 to the y is equal to 0. In other words, what power do I need to raise 2 to in order to get 0? If you're graphically minded, you can kind of imagine the graph of 2 to the x we did last week has this horizontal asymptote. It never actually approaches 0. Right? 2 to any power will never be 0. If you want to do some numerical estimates, well, what happens if I start plugging in negative values for y? So like negative 1 will give me 2 to the 1/2, or 2 to the minus 1, which is 1/2. Negative 2 gives me 2 to the minus 2, so 1/4. As we plug in bigger and bigger negative numbers into that y, negative 1,000. 2 to the minus 1,000 is going to be a very, very small fraction. It'll get closer and closer to 0, but it will never actually hit 0. So this is undefined. So I'll write UND for undefined. In calculus, a better example for this, better number to put in, or a better expression, would be minus infinity. And learn to deal with the infinities in calculus. Maybe we'll talk about it a bit at the end of the semester once we introduce limits. So this kind of confirms that we can't have a 0 in there. And likewise, you could use the same reasoning of what happens if x is a negative number. It's not going to exist. So we've got this vertical asymptote on the y-axis. Let me go ahead and scale the axes as well. I'm going to put the x scale a little bit smaller, the y scale a bit bigger. And we've got those dots on the y-axis. Let's go ahead and compute some more points. So x equals 1, we'll have log base 2 of 1. And what does this say? 2 to the y equals 1. And so y has to be 0. This confers that our x-intercept is always 1 if we're not shifting or anything like that. Log base 2 of 2. Wrote that one wrong. So same base, 2 to the y equals 2. So y equals 1. And then, let's see, we can do a couple more. We'll have log base 2 of 4. So, excuse me, this is x equals 2. This one's x equals 4. And this will say 2 to the y equals 4. So y equals 2. The last one, I'll leave you to check on your own. We should have the point 8, and our y will be 3, because 2 cubed is 8. So you can kind of see what's going to happen. This minus infinity at 0 essentially implies that as I'm getting closer and closer to 0, we're down here. We're going to trace the asymptote down the minus infinity. And we're going to come up and then connect the dots. And you can kind of see what's happening. It's stretched vertically a little bit because the y-axis, I scaled it much wider than the x-axis. But you can kind of see how quickly it starts to taper off, and then it grows. It will always be increasing for a base bigger than 1, but it's going to start to grow really slowly. And the x-axis, you'll have to stretch out really far on the x-axis to get that next one. All right, so let's graph one more real quick. Let's say y equals log base 1/3 of x. So I'm only drawing this right half of the graph because for our domains we saw are 0 to infinity. So we don't have any negative numbers to plot on the x-axis. Again, now at x equals 0, we will have y is log base 1/3 of 0. So 1/3 to the y is equal to 0. But now because 1/3 is a fraction, you want to think of it as, well, what's 1/3 squared? 1/9. What's 1/3 cubed? 1/27. So now as y gets bigger and bigger, it'll approach 0. So our asymptote, still x equals 0, still the y-axis. But now we're coming in from the top. I drew this slanted a little bit. Here, let me just redraw it. Draw it down here. So we've still got our y-axis. We are coming down from the top. Our x-intercept is still 1. And let's pick one more point. So let's say x equals 3. Now let's do 3 and x equals 9. Do 2 more points. So we will get y as log base 1/3, 3. which asks what y needs to be when I raise 1/3 to the y in order to get 3. Oops, sorry, I'm off the screen there. And since this 1/3 is a fraction, hopefully you recognize that y is -1 in this case. And in this case, when x is 9, we'll have y is equal to log base 1/3 of 9, which asks what power do I need to raise 1/3 to in order to get 9? And that power is -2. The negatives will take the reciprocal of 1/3, which will give me 3, and then 3 squared is 9. And of course, 3 to the 1 is 1, or 3. Okay, so let's plot these. We've got 3, -1, and then 9. I think I started to stretch my scale there a little bit. 9, 3, -2. So right there. And then so we'll come down, trace that, and then it starts to broaden out. It'll be decreasing now, right? So remember, when the base is a fraction, it will be decreasing and negative. Now you should notice that, how do these graphs look? So when we saw exponentials, what happened if we had a negative base? A negative base with exponentials flipped the graph horizontally. And I think we saw an example of that. With the inverses, a negative base, or excuse me, a fractional base flips it vertically. So here's a log base 2. If I were to graph log base 1/2 of x, it would essentially take this graph and flip it vertically. And it would look similar to this, of course, not as flat, because we'd still have more points in there we could plot. And the way you can really see this is just by doing a little bit of this arithmetic practice that we've been doing. If we have this equation, y is equal to log base 1/3 of x, and if we don't like that 1/3 base and want to write it as a whole number, well, rewriting this equation says 1/3 to the y should equal x. But now 1/3 we can write as 3 to the -1. So in other words, 1/3 to the y, we'll have 3 to the -y is equal to x. All these equations are the same. And now let's move it back into logs. How do I turn an exponential into a log? It's always going to be log of the same base, now again of the opposite side of the equation. Log base 3 of x is equal to the exponent. So all of these expressions imply the same thing, and of course now we can multiply that negative over, and so y is equal to negative log base 3 of x. So now you can kind of see how, if I started with log base 3 of x and did a vertical flip, we would get this exact graph. Any questions on any of that? All right.